Okay, so back to the pizza recipe. We talked about this recipe for a pizza: 1 crust, 5 ounces of sauce, 2 cups of cheese, and 1 pizza. Well, what if we have these ingredients? 4 crusts, 10 cups of cheese, 15 ounces of sauce. How many pizzas can we make? So how did you do that?
It takes 5 ounces of tomato sauce, you only have 15.
And do you have enough crusts to make 3 pizzas and enough cheese? Yeah. So what we do to figure it out, and he did this very quickly in his head, because this kind of stuff makes sense to us, is we're looking at 4 crusts, how many pizzas? 4 pizzas. 10 cups of cheese, how many pizzas? Well, I need 2 for each, so 5 pizzas. 15 ounces, I need 5 for each, so 3 pizzas. And we understand that once we make 3 pizzas, we run out of sauce. We're done with pizza making till we go to the store, right? It's the same process with a chemical reaction, but it tends to be more confusing because it's not something we're familiar with. So doing a problem like this is walking on the sidewalk with grass on both sides. And when we do the chemicals, it's walking on the same sidewalk, but now it's over the Grand Canyon and there's no rails. And we're like, right? Same process, but it feels different. So we're going to look in probably too much detail at how we did this in our heads so we can apply that to the chemical problems. So the approach here is to take each of the ingredients and figure out how much product, how many pizzas can we make. So 4 crusts. From the recipe, I see that I can make 1 pizza from 1 crust. And I'm getting these numbers from this recipe, which looks an awful lot like a balanced chemical equation, right? So these units cancel out. 4 pizzas. And then I look at the next ingredient. 10 cups of cheese. And I ask myself, well, how many pizzas to how many cups of cheese? I can make 1 pizza for every 2 cups of cheese. 1 pizza for 2 cups of cheese. Cups of cheese cancel out. 5 pizzas. 15 ounces of sauce. Our equation recipe shows 1 pizza takes 5 ounces of sauce. 1 pizza, 5 ounces. Sorry about that. The ounces of sauce cancel out, and I get 3 pizzas. Do I add those numbers together to tell how many pizzas I can make? That doesn't make any sense, does it? I'm going to choose the smallest one, right? Because I recognize that once I make 3 pizzas, I've run out of this ingredient. What happens to the rest of the cheese and the crust? Put it back in the fridge, right? It's just left over. So the smallest number is how many we can make. Everybody cool with that? You could make cheesy bread, yeah. So here it is with pictures. So 4 crusts, we could make 4 pizzas. 10 cups of cheese, we could make 5 pizzas. 15 ounces of sauce, we could make 3 pizzas. This is the smallest amount of product, the least amount of product. This is what limits our production of pizza, right? If we had more sauce, we could have made at least 1 more pizza. We call this the limiting reactant or the limiting ingredient. And this is very common when you're cooking, right? That if you want to just keep making whatever you're making, usually there's one thing you're going to run out of first. you run out of eggs or you run out of butter, and you've got plenty of flour, there's lots and lots of salt, but you ran out of eggs, so you have to stop, right? That happens in a chemical reaction as well. So here we're saying that tomato sauce is the limiting reactant, or sometimes we call it the limiting reagent. It's the reactant that makes the least amount of product. The maximum number of pizzas we can make is the theoretical yield. So that's the amount of product we can make in a chemical reaction based on the amount of limiting reactant. The ingredient that makes the least amount of pizza, the limiting reactant, determines how many pizzas you can make, the theoretical yield. So in chemical reactions, it is also likely that one of the reactants will be used up before the others. When that reactant is used up, the reaction stops, just like the pizza making process stopped when we ran out of sauce. So the reactant that limits the amount of product is called the limiting reactant. The limiting reactant gets completely consumed, gets used up. The other reactants are said to be in excess. We have extra of them. The actual amount of product made in a chemical reaction is called the actual yield. The actual amount is the actual yield. The terms we use are not intended to be confusing. We're trying to be descriptive here. So let's think about the pizzas. You're making pizzas, and sometimes something happens, right? You could get distracted while one's in the oven, on TikTok or something, and you didn't hear the timer until you smell or hear the fire alarm, the smoke alarm, right? You're like, dang, I burned that one. And you pay more attention to the other two, and you end up with 2 pizzas. But you had enough stuff, you should have been able to make 3 pizzas, right? Or maybe you drop one on the floor. The dog gets it, right? Stuff like that happens, right? So the actual yield is how much actually gets produced. The theoretical yield is if everything went perfectly, I could make this much. Doesn't always happen that way. So we use percent yield to express the efficiency of a reaction or the efficiency of making pizzas. And so we calculate the percentage of the theoretical yield that we actually make. And so this is the equation, which is just a regular percentage type equation. The percent yield is the actual yield divided by the theoretical yield times 100. It's the amount we have out of the amount we possibly could have had. So if you have 100% yield, that means everything went great, you made the most possible. If we dropped 1 pizza out of 3, then we'd have 2 pizzas out of 3, and we'd have a 67% yield, right? And if you're working at Domino's or something, they're not going to be real happy with you. So this is a summary of these terms. Limiting reactant is completely used up. It limits the amount of product, limiting. The reactant in excess, we have extra. The theoretical yield, how much can be made based on the amount of the limiting reactant. Actual yield, amount actually produced, and then the percent yield equation there. Yes?
So in our thing that we did yesterday, the limiting reactant would be the zinc, or reactant excess would be the zinc,
Yes.
but not. But what was the limiting thing?
The iodine.
Okay, that.
Yeah. So on Tuesday, still having problems with days. On Tuesday, we mixed zinc and iodine together in methanol and heated it in the hood until it turned colorless. And then we recovered the leftover zinc. There was extra zinc. All of the iodine got used up. That was the limiting reactant. Great application. So we could calculate a percent yield or something, but that experiment isn't set up for that. So let's look at our combustion of methane reaction that we looked at before. So this gives us the ratios of the different parts, right? Just like the pizza recipe. So we need 1 molecule of CH3 and 2 molecules of O2 to make 1 molecule of CO2 and 2 molecules of water, right? We can also take this chemical equation and express it in terms of dozens or moles, which are chemist dozens, just a much, much bigger number. So we're going to stick with just the number of particles for a few minutes. What if we have 5 molecules of CH4 and 8 molecules of O2? It's the same as the pizza problem. We're going to take each ingredient, each reactant, and see how much product can I make. So if I had 5 molecules of CH4, this is telling me that I could make 1 molecule of CO2 for every molecule of CH4. So I could make 5 molecules of CO2. That would be assuming that I had enough oxygen. Then we look at the other one. We had 8 molecules of oxygen, and we get 1 molecule of CO2 for every 2 moles of oxygen, and so that gives us 4. So from the oxygen, we can only make 4 molecules. From the CH4, we could make 5. So just like with the pizzas, things stop at the smaller amount of product. So this is the least amount of product. That's our theoretical yield. This is our limiting reactant. And the other thing is in excess. Any questions? So a conceptual problem. Nitrogen and hydrogen gas react to form ammonia according to the reaction. So 1 nitrogen and 3 hydrogen molecules make 2 ammonia molecules. A flask contains a mixture of reactants. Keep dropping that. Represented by the image shown at the left. Which of the following images best represents the mixture in the flask after the reactants have reacted as completely as possible? So I have C as the answer. Let's think about, well, how could we do this? Because we're not going to actually do any calculations here, but I can use this picture, and I need 1 nitrogen and 3 hydrogens. So here's 1 nitrogen and 3 hydrogens. That could make 1. And here's another nitrogen, and so that's going to take 3 hydrogens. And then I'm going to have these 2 guys left. So then I'm looking at which of the flasks matches up with that. So this is going to give me 2 molecules of ammonia, and this is going to give me 2 molecules of ammonia. And then I've got these 2 left over, right? And so the answer is C. Any questions? So when we're given quantities as masses, which is typically what happens, we have to calculate the moles of product that can be made from each reactant, use the smaller moles of product to find the mass of the product. So this is the plan of attack given in the textbook, and this is an entirely valid way of doing it. And if this makes sense to you, you go right ahead. I'm going to show you something that maybe takes a tiny bit longer, but requires less thinking, right? So this is what I prefer to do. So I'm going to change this up a little bit. I'm going to get rid of that. So you're just going to take this to grams of MgO. And you're going to take this one to grams of MgO. And choose the smaller. So I have two reactants. I have magnesium and I have oxygen. I'm going to take the magnesium, grams to moles to grams of product. I'm going to take the oxygen, grams to moles to grams. Just like with the pizza, but it's more steps. And then I'm going to just see which of these is smaller, and that's my theoretical yield, my mass of product. Okay? So that's how I'm going to do the problems. There are other ways, but they tend to be confusing to a fair number of students, and so I'm not going to talk about them.
I'm sorry, you said use the smaller one. We're using the smaller answer we get from in grams?
Yes. Yeah. Because what we did earlier is we were just looking basically at here in the middle where we're thinking about numbers of things. And we recognize that with the pizzas, when we run out of an ingredient, we stop. So it was the smaller number of pizzas. So here it's the same idea, but we're going to go all the way to find the grams of product. And the smaller one is where the reaction will stop. Because let's say this is the smaller one. This one might be able to make more, but I don't have enough oxygen. When the oxygen runs out, the reaction stops.
Because you have it on the bottom that says use the smaller moles of product to find the mass. Was that to the other graph you had?
Yeah.
Okay.
Here. There. Is that better?
Yeah.
So use the smaller mass of products. Actually, the smaller mass of products is the mass of products.
Oh, okay.
Yeah. Just make sure I didn't skip anything. Okay, let's do a real problem here. This is the magnesium and oxygen. Reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What is the limiting reactant and the theoretical yield? Suppose that the actual yield is 55.9 grams. What is the percent yield? Like so many questions, right? Pull the numbers out. So we've got grams of magnesium, we have grams of oxygen. So let's just deal with that. So I'm going to use my balanced chemical equation to organize this information. So this is 42.5 grams of magnesium, and this is 33.8 grams of oxygen. And it's not super clear, but what am I trying to find out?
You're trying to find the limiting reactant theoretical yield.
Mm-hmm.
Actual yield is 58.9 grams. And then you find the percent yield after that.
Let's, what color would be good? Let's try blue. So I need the limiting reactant. I need the theoretical yield. And it's unfortunate that that's split across the line, but the theoretical is the percent yield. Nowhere does it say find the grams of magnesium oxide. But what is our product? This is our product, right? And so the theoretical yield is how much of this can we make, right? And it doesn't specify the units. Kind of don't like that about these problems, but what do we usually find stuff in? We're starting with grams of reactants, and we would usually end up with, well, grams to moles to grams. So let's find the grams of magnesium oxide. And how do we get the theoretical yield from that? Well, what I'm going to do is I'm going to take the mass of this reactant, grams to moles to grams of magnesium oxide. And I'm going to take the mass of the other reactant, grams to moles to grams of magnesium oxide. Just like in that previous slide, you take each reactant to grams of product, and then just pick the smaller one. Okay? So I like to start with the first one because it's first. So 42.5 grams of magnesium oxide. Grams to moles to grams. So grams of that to moles of that. Thank you. It is just magnesium. There, it's just magnesium. Good job paying attention. Moles of magnesium, 2 moles of what? Magnesium oxide. This is where I'm trying to go. Moles of magnesium oxide. And then I'm going to go to grams of magnesium oxide. So grams of magnesium down here. Moles of magnesium down here. Moles of magnesium oxide down here. The mole ratio, what do I put in front of MgO? 2. And what do I put in front of Mg? 2. So these are the coefficients. 2 moles of magnesium, 2 moles of magnesium, 2 moles of magnesium oxide, 2 moles of magnesium oxide. Then I need molar masses. Magnesium is what, 24.31? Is the mass of 1 mole. That's an element, so it's just straight off the periodic table. And then I need the mass of magnesium oxide, which would be 24.31 plus 16, which is what, that's 40.31? Did that in my head. Ooh. I don't recommend that. 40.31 grams per mole. And so I calculate this. 42.5 divided by 24.31 times 2 divided by 2 times 40.31 equals. And I'm always thinking about significant figures. My initial number had 3, and so my answer here is going to have 3, but I'm going to write down the next 2 for safety. Grams of magnesium oxide. But just like with the pizzas, I'm going to find out how much product from each reactant. So I'm going to do this again with the other reactant.
If there was an additional reactant, would we do it 3 times?
If there were 3 reactants, you'd have to do it 3 times. Yep. So grams of oxygen. I'm going to go grams to moles to moles to grams. I'm going to the same thing. When I was doing the pizzas, I took the numbers of crusts and I found out how many pizzas I could make. And then the amount of sauce, how many pizzas. I didn't take the amount of sauce and find out how much cheese I needed. I wanted to find out how many pizzas I can make. So grams of oxygen to moles of oxygen to moles of magnesium oxide. Oops.
So that number 70.472, that's telling you how much MgO you can make if oxygen was not a factor?
Yes.
Okay.
This is the amount of magnesium oxide I could make from this amount of magnesium if I had plenty of oxygen. But we don't know from these numbers, and because of the different masses of moles and the different mole ratios, we can't just say, well, this is the smaller number, it's going to be limiting. We have to do the calculation. So then we're going to ask the other question, well, from this much oxygen, if I have plenty of magnesium, how much product can I make? So I got grams to moles to moles to grams. I got grams of MgO down here. No. I zoomed out too far and I got lost. I zoomed in too far. I want grams of O2 down here, moles of O2 down here, and moles of MgO down here. We want to make sure that our units really are canceling out, because if we get the units in wrong, everything's going to be wrong. So my mole ratios in here, 2 magnesium oxides, so 2 moles of magnesium oxide. How many moles of oxygen? 1. And then I need the molar mass of oxygen, 32. It's 16 and 16. And then over here, I need the molar mass of MgO. But look, I already did that. This last term is going to be the same every time, because you're going to the same amount of product. The same product. So what the book had you do was stop here, identify the smaller, and then finish. I say, since we're doing the last step the same on both, let's just go all the way on both. Not much extra work. And then we have the answer, it's just the smallest one. 33.8 divided by 32 times 2 times 40.31. $85.154 grams of MgO. Now the really hard part. Which number is smaller? The top one, right? 70 is smaller. So this is how much product we could make. Because once we come to 70.472 grams of magnesium oxide, we have run out of magnesium. There's more oxygen, but we can't keep making it because we're missing an ingredient. Just like with the pizza, we ran out of sauce, we had to stop. Because it isn't pizza without sauce. So the theoretical yield would be 70.5 grams, using the correct number of sig figs there. What's the reactant that limits how much we can make? Magnesium. So I've got the smaller number here, and I go back, what ingredient, what reactant gave me that? That's my limiting reactant. So limiting reactant, magnesium.
Like test-wise, we don't have to state for the 70.5 grams that it's magnesium oxide. We just leave it as grams.
Well, it would not be critical to state that it's magnesium oxide, but I would put it on there. I think it's always good to label things. Now, what about this actual yield business? Did we need that to calculate the theoretical yield? Yeah, we need that for the percent yield. So actual yield is 55.9. And it says, what's the percent yield? Well, we had an equation for that. The percent yield is equal to the actual yield divided by the theoretical yield. I like to call him Theo, times 100. In a problem like this on a book, on a test, on a worksheet, they have to tell you what the actual yield is, because you have no way of knowing otherwise. Like, you've got all these ingredients for pizza. How do you know how many actually got made? Well, the person making the pizzas has to tell you, right? So the actual yield has to be given to you somewhere. So the actual yield is 55.9 grams. The theoretical yield is 70.5. I prefer to use this one with extra digits. just to avoid rounding errors, and times 100. So 55.9 divided by 70.472 times 100, and that's also going to have three significant figures. 79.322%. So my percent yield, I would round that to three significant figures, 79.3%. Any questions? There's lots of pieces. Things got kind of complicated fast, huh? Each individual piece is pretty straightforward. What gets confusing is, how do I string these together to get the right answer? And it takes practice. Oh, good, I got the answers right. Let's do another one. Ammonia can be synthesized by this reaction. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of H2 and 31.5 kilograms of N2? Well, there's the kilograms again. Well, let's write these masses down. It's telling me 5.22 kilograms of hydrogen. Whoops, that's kind of messy. Kilograms. 31.5 kilograms of nitrogen. And I want to know how many kilograms of ammonia. I'm given the mass of both of the reactants. That tells me it's a limiting reactant problem. So I'm going to take the one reactant and calculate amount of product. I'm going to take the other reactant, calculate the amount of product. The smaller is my answer.
Would there be an example where we're given like the mass of the product and not the mass of the reactant? In that case, would we just subtract one of the reactants from the mass, or do we have to do other calculations to find the reactant?
You'd have to do other calculations. Otherwise, it would be one of those. The law of conservation of mass problems are where you can just subtract and get answers. But those are actually usually pretty special cases where we have just the right amount of stuff, which almost never happens. Yeah. Well, yeah.
In case we get buried in the calculation, is there a way to determine if the product side is at the denominator and the reactants are on the numerator? Is there some kind of trick to that?
Well, we're always going to end up with the product. I mean, this is what we're trying to find. So we need to end up with that in the numerator.
No, I mean, like when you're doing the calculation, so let's say if there was 2 nitrogen, so we know it's on the product side, on the reactant side, so is that going to be like on the numerator, or when you're doing the conversions from mole to?
When we're doing the units, well, in the numerator is always going to be grams to moles to moles to grams. And then those units slide down and over, if that makes sense. So what should we do with a kilo here? Just leave it? Change it to grams. So I'm going to show you the 2 other ways. The first one is just do everything. So that's kilograms to grams to moles to moles to grams to kilograms. Because we're starting with kilograms and we're trying to find kilograms. So 5.22 kilograms of hydrogen. And I want to convert that to grams of hydrogen. So I can do grams to moles to moles to grams. And then I'm going to go to moles of hydrogen. And then moles of product, NH3. And grams of NH3. And then kilograms of NH3. So this part in the middle, grams to moles to moles to grams, that's what we were doing before. We've added something on the beginning and we've added something on the end. Sometimes that happens. I need this kilograms of H2 to cancel out. So kilograms of H2 comes down here. Those units cancel. Grams of H2 comes down here. So it cancels. Moles of H2. Moles of NH3. Grams of NH3. Any questions? So I've got all these terms in here. They need numbers. I'm going to do the moles in the middle. Moles of NH3. This comes from the balanced chemical equation. You get 2 moles of NH3. So 2 moles of NH3 from 3 moles of H2. This is the only place that those coefficients get used. We only use them once. We don't need to use things over and over and over again. How about the molar mass of hydrogen? Yeah, it's 2 times 1.008, or 2.016 grams. Bless you. So 1 mole is 2.016 grams. And then over here, I need the molar mass of ammonia. So that's 14.01 plus 3 times 1.008. $17.034. 17.034 grams of ammonia is 1 mole of ammonia. I need the relationship between grams and kilograms here. Kilo stands for times 10 to the 3, right? So here I've got grams and kilograms. 1 kilogram is 1 times 10 to the 3rd grams. I put the kilo on one side, the times 10 to the 3 on the other. Over here I've got the kilo in the numerator. 1 kilogram and 1 times 10 to the 3 down there. So now it's plug and chug. So 5.22 times 1 EE3 divided by 2.016 times 2 divided by 3 times 17.034 divided by 1 EE3 29.403 kilograms NH3. So I'm multiplying by 1 times 10 to the 3, and I'm dividing by 1 times 10 to the 3. Those cancel out, don't they? Does it hurt to write them in there? Is it wrong? No? Some people like to go the long way because they remember it and it's comfortable and it's easy instead of trying to take the shortcut. Sometimes when we take a shortcut, it doesn't work out very well, right? So if you're good at the shortcut, by all means use it, but if you aren't, take the long way and get it right. Are we done? No, we're like half done. These problems get kind of long. Now we have to look at the other ingredient, the other reactant. 31.5 kilograms of N2. So I'm going to show you a slightly different way to deal with the kilo here. I'm going to write that kilo in red. Kilo really is a number. It's times 10 to the 3. And so what I'm going to do is I'm going to cancel grams of N2. I'm not going to cancel the K. I'm going to let it sit there. So it's in red. I'm going to just not pay attention to it right now. So grams to moles to moles to grams. So, wrong green. So grams of nitrogen to moles of nitrogen to moles of ammonia to grams of ammonia. I'm going to put grams of N2 down here. Grams of N2 cancel grams of N2, doesn't cancel kilo. Moles of N2 cancels moles of N2. Moles of NH3 cancels moles of NH3. Moles in the middle, 2 moles of NH3. How many moles of N2? Just 1, right? Molar mass of N2. Well, it's not too hard. Yeah, 28.02, because it's 2 times 14.01. So 1 mole is 28.02 grams. And then this one at the end, same molar mass, 17.034. Grams is 1 mole. So let's do the numbers. 31.5 divided by 28.02 times 2 times 17.034 equals 38.299. So I have, I guess yellow would work. I have this unit that's not canceled out, right? Grams of NH3. But what else didn't cancel? Did I cancel this? I didn't. It's still sitting there. It's still there. Didn't cancel it out. So that's another way to think of the kilogram, gram, mole, gram, kilogram thing.
That doesn't affect, like, when you take 28.02 grams of sodium or nitrogen?
No, it really doesn't. Because this part is really 31.5 times 10 to the 3. right? Because that's what kilo means, times 10 to the 3. I canceled out the grams of nitrogen. I didn't cancel out the times 10 to the 3. And so then over here, I still have that times 10 to the 3, which is kilograms. So this is really cool for some people. And other people are like, what the heck are you doing with that? Do this then. This always works. The top one always works, right?
Well, the takeaway, you don't ever have to unit convert when you're doing a reaction.
The only time you have to convert units is if the units that you're given, and if it's not given in grams, then when we get the molar mass, we always think of it in grams per mole. And so we somehow need to deal with that. So here it was kilograms. Well, 1 mole is 28 grams. I can't say that 1 mole is 28 kilograms. If I wanted to, I could say a kilomole is 28 kilograms. A kilomole. Like whack-a-mole, a kilomole. It's a chemistry game. So, all that aside, what's the theoretical yield?
29.4.
Yeah, it's the 29. It's the smaller of the numbers. So, the theoretical yield tie, is equal to 29.4 kilograms of NH3. When you do problems like this on a lab or a worksheet where you're writing it out on paper and giving it to me, it's important, or on an exam if it's a show your work problem, it's really important to not stop before I get to identifying this in orange. You can do the calculations and come up with these answers, and the work is beautiful, but if you don't choose one of them, you can't get full credit, right? Because you haven't actually answered it. You need to circle it or write it like this, somehow specify this is my answer. On a multiple choice exam, we don't have that problem because you just pick one of the choices. But written out, I sometimes see that. People do this beautiful work, but they never actually picked an answer. Any questions? $29.4 kilograms. Here's another one. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of FTO3 with 85.8 grams of CO produces 72.3 grams of Fe. Determine the limiting reactant, theoretical yield, and percent yield. So I can take these masses and write them under the corresponding pieces in the equation. 167 grams of the CO, I've got 85.8 grams. And then it says 72.3 grams. So I'm just kind of on a roll and I'm writing stuff down. I have masses for 2 of the reactants. A lot of the problems, we're not going to make you do limiting reactant problems all the time. But you'll notice the wording is usually careful. They'll say this much FTO3 with an excess of CO. They'll specify somehow that you don't have to worry about the other one. Here, we're giving you masses of both, and that's a big clue. We have to do the calculation with both. Why did they give me the mass of iron then? So I can calculate the percent yield. Because what this is, that's the actual yield. It said this reaction produces this. So Joe Schmo had 10 crusts and 15 ounces of sauce and 2 cups of cheese, and he made 2 pizzas. Does that mean that's all you can make from those ingredients? No, that's all that he made. We don't know what happened to the other pizza, but something did. It's giving you the actual yield. So I don't really want that in there. I'm going to move it. I'm going to put it over here. Actual yield is that. I'm trying to find the mass of Fe. Now this problem, there are 2 products. We could calculate either one. Why do I want to calculate the mass of iron and not CO2? Because they gave me a mass of iron. And up here it says to obtain iron from iron ore. The iron is the part that we're interested in. We're not interested in making CO2 here. So it's telling me a mass of iron. I need the theoretical yield of iron. So nicely, this is one in grams. So I'm going to do 2 calculations of grams to moles to moles to grams. Grams of Fe2O3 to moles of Fe2O3. To moles of Fe to grams of Fe. Grams of Fe2O3 are down here. Moles of Fe2O3 are down here. Moles of Fe are down there. It's a bit repetitive, isn't it? It's like always this, the units are the same, it's just the compounds that are different, the elements. So I have moles in the middle. 1 mole of Fe2O3 gives me 2 moles of iron. So 1 mole of Fe2O3 to 2 moles of iron. I'm going to do this one next because it's easier. 55.85 grams of iron is 1 mole of iron. And then I have to calculate for the Fe2O3, 2 times 55.85 plus 3 times 16. $159.7. 1 mole, 159.7. So 167 divided by 159.7 times 2 times 55.85. Three sig figs again. So there's one possible answer, and I do another calculation with the other reactant. So the other reactant is the the carbon monoxide. 85.8 grams of carbon monoxide. Grams to moles to moles to grams. So grams to moles to moles to grams. Mole ratio 3 moles of carbon monoxide to 2 moles of iron. This last molar mass is the same. And then I need to calculate this one. Carbon is 12.01, oxygen is 16, I think that's 28.01. 1 mole is 28.01 grams. 85.8 divided by 28, oops, 0.01 times 2 divided by 3 times 55.85 equals 114.05 grams of iron. What's the limiting reactant? The CO. The limiting reactant is the one that makes the smallest amount of product. So what's my theoretical yield? It's the smallest amount of product. 114 grams of iron. And then they want the percent yield. So percent yield is the actual yield over the theoretical yield. Actually, I don't like that. Actual over theoretical times 100. They told me what the actual yield was because that's the only way I'm going to know what it is. I'm going to divide by my theoretical yield, multiply by 100. .4%. I was asked to find 3 things. I get my limiting reactant, my theoretical yield, which, maybe theoretical yield, and this is my percent yield.
You do sig figs on percentages also?
You do sig figs on percentages also. This 100 is an example of an integer part of an equation. So that 100 is an exact number. So when I'm doing the sig figs for this calculation, I'm looking at how many significant figures in the 72.3, how many in the 114.05. And they both have 3, so my answer has 3. Any other questions?